In the beginning, there was darkness, a silence so profound that even memory could not hold it. And then light, a wave, a spark, a beam slicing through the infinite void, illuminating creation itself. Since that first instant, light has been the universe's messenger, carrying the stories of stars, galaxies, and the birth of time itself. It travels unfaltering, a cosmic thread binding past to present, shaping the limits of what can be known. For more than a century, physicists have treated this speed as sacred, the barrier that no object, no particle, no dream can cross. To move with light is to touch the edge of reality itself. But what if humanity dared to press against this final frontier? What if, in pursuit of the stars, we attempted to travel at the very speed of light? Would the universe remain silent, unchanged? Or would the act itself fracture the cosmic order? Some theories whisper of paradoxes so severe that time itself could twist. Others warn of energies so violent they could unravel the very fabric of spacetime. Could a single vessel, a single experiment, trigger the collapse of everything we know? The dream of light-speed travel is not merely about exploration. It is about trespassing into forbidden physics, tampering with the foundation upon which existence rests. Tonight, we step into that paradox, into the dangerous beauty of light itself. Stay with us as we uncover why the greatest dream of interstellar travel may also be the seed of cosmic destruction. Subscribe and join this journey through science, philosophy, and the fragile threads that hold reality together. Since the first flicker of human curiosity, the horizon has never been a boundary, it has been an invitation. In ancient deserts, riders pushed their horses to collapse, racing not simply to arrive, but to outpace the sinking sun. Sailors once chased winds across uncharted oceans, believing new worlds waited just beyond the edge of the map. And when the steam engine roared to life, the train became a moving boundary of time itself, shrinking continents into mere days. The story of humanity is the story of acceleration, always faster, always farther, always reaching beyond the line. That yesterday drew dot, then came the age of rockets, the thundering ascent of metal giants that clawed their way past Earth's grip and kissed the void of space. For the first time, the horizon was no longer on Earth, it was the stars themselves. The moon was reached, planets mapped, galaxies glimpsed through the eyes of telescopes. And yet, amid these triumphs, a realization loomed larger than any distance. Travel. The stars were impossibly far. Alpha Centauri, the nearest neighbor, stood 4 light-years away. That is 25 trillion miles, so vast that even the fastest spacecraft humanity has ever built. Voyager 1 would need more than 70,000 years to arrive. Our galaxy, the Milky Way, spans 100,000 light-years, and beyond it, billions of other galaxies float in a silent ocean of darkness. It was here, in the collision of ambition and reality, that light itself emerged as both savior and jailer. For light does not merely illuminate, the cosmos defines its very architecture. At 299,792 kilometers per second, it sets the ultimate boundary of motion, a cosmic decree written into the mathematics of space and time itself. Albert Einstein revealed this truth in 1905. His theory of special relativity reshaped physics with one radical statement: nothing with mass can reach, let alone exceed, the speed of light. Space and time are not passive backdrops. They bend, stretch, and conspire to enforce this limit. As velocity grows, time dilates, length contracts, and mass inflates toward infinity. To approach light speed is to wage war against reality itself. And reality will not yield. And yet, the dream persisted. Science fiction ignited it into flame. The pages of Jules Verne, the visions of H.G. Wells, and later the luminous screen of Star Trek transformed this impossibility into story. Warp drives bent space-time like a sail catching winds of the cosmos. Wormholes bridged distant galaxies with tunnels of invisible geometry. Generations watched as starships leaped between suns as casually as ships once crossed seas. Imagination is not bound by equations. It thrives in defiance of them. And for humanity, this defiance carries weight, for the yearning to escape Earth is not simply wonder, it is survival. The Earth is fragile, a thin crust above molten fire, wrapped in an atmosphere so narrow it could be crossed in the span of a day's drive. Asteroids have struck before, ending the reign of the dinosaurs. In a single instant of planetary violence, the sun itself will swell and die, scorching the Earth into a barren husk. Even without catastrophe, the hunger for growth, for discovery, for destiny presses outward. If humanity is to endure, it must step beyond its cradle. The stars call not only to curiosity, but to necessity. And so, the speed of light is no mere number. It is the wall between humanity and its future. To live among the stars, to colonize other worlds, to ensure survival against the silence of extinction, this wall must be broken, or at least bypassed. But here, the story turns. For if the dream of light speed holds the key to survival, it may also hold the seed of destruction. The equations whisper warnings. If matter could somehow accelerate to light speed, its energy would surge toward infinity. The very act could destabilize the fabric of space-time, releasing distortions not yet imagined. Even the notion of faster-than-light travel raises paradoxes that gnaw at reason. Signals arriving before they are sent, causes undone by their effects. Reality looping back upon itself. Could chasing the stars summon not a new beginning, but an ending? Could the attempt to move as light does unravel the universe's delicate balance? This is the paradox at the heart of humanity's greatest ambition. The dream of light-speed travel is not simply about ships and engines. It is about daring to touch the most sacred law the cosmos has written, a law that binds galaxies, governs time, and anchors existence. The tension sharpens here between destiny and danger. To surrender the dream is to accept confinement to a single world, vulnerable to chance and time. To pursue it is to court consequences, too vast to predict, too dangerous to imagine. This is why the question matters. It is not only a question of science, it is a question of survival, of philosophy, of the fragile future of life itself. And so the chapter closes where it began, with humanity gazing beyond its horizon. Horses collapsed in desert sands, sails filled with winds that could betray, rockets bursting through skies. Always farther, always faster. Now the horizon is light itself, a horizon that does not recede but stands unyielding, daring us to try. The dream remains, the question deepens, and the danger begins. The dream of outrunning light was not born in fiction alone. It grew in the laboratories, in the observatories, in the restless calculations of physicists who dared to press against nature's boundaries. The 20th century was an age of revelation. For the first time, humanity could measure the universe with instruments that pierced beyond the naked eye. Radio telescopes caught whispers from quasars at the edges of time. Particle accelerators hurled atoms to near light speeds, tearing apart matter to glimpse the secrets within. The pursuit of speed was no longer metaphoric. Light was physical, real, carved into the circuits of machines and the chalk marks of equations. And in those equations lay brutal truth, Einstein's special relativity had already drawn the line. Nothing with mass could reach the velocity of light without infinite energy. Yet scientists tested the edges of that decree. They built accelerators, colossal rings of steel and magnetism, like the Large Hadron Collider beneath Geneva. Within these machines, protons raced to 99.999999% the speed of light. Their lifetimes stretched, their masses swelled, exactly as relativity predicted. No law was broken. The barrier held firm. The closer humanity came, the more unyielding the wall appeared. But science is not a monolith. Where relativity enforced its dominion, new theories began to probe its edges. Quantum mechanics revealed a universe stranger than any myth. Particles did not behave like solid stones. They shimmered as probabilities, existing in many states at once, collapsing only when observed. Some even seemed to tunnel through barriers they had no right to cross, vanishing on one side and reappearing on the other. Could such phenomena hint at shortcuts through spacetime itself? Speculation began to grow, not from fantasy, but from mathematics. In 1994, a Mexican physicist named Miguel Alcubierre proposed an audacious idea: the warp drive. Not a ship moving faster than light, but space itself bending around it. His equations, rooted in Einstein's own field equations, described a bubble of spacetime that could contract ahead and expand behind, carrying a vessel forward at superluminal speed without locally breaking the light barrier. In theory, the ship would remain motionless within the bubble, untouched by relativistic limits, while the fabric of reality itself carried it forward. It was a vision torn from the pages of fiction, yet written in the language of physics. But the equations carried a catch. To function, such a warp drive would require exotic matter substances with negative energy density, unlike anything ever observed in nature. To form even a modest bubble, the amount of energy demanded was staggering, greater than the mass of entire planets. And so, like a mirage, the dream shimmered at the edge of possibility, tantalizing but unreachable. Still, the search did not stop. Wormholes, once dismissed as mathematical curiosities, re-emerged as candidates for cosmic bridges. If space-time could fold, perhaps two distant points could connect, like tunnels through the fabric of reality. Black holes, with their infinite gravity and warped horizons, hinted at gateways where the ordinary laws of distance might collapse. Could a civilization, advanced enough to tame these monsters, leap across the stars in a single instant? NASA itself joined the speculation. In 2012, a small research group called EagleWorks, led by physicist Harold White, explored ways to reduce Alcubierre's impossible energy requirements. They imagined new geometries, toroidal rings that might shrink the need from planetary scales to something merely astronomical. Though no experimental progress emerged, the effort revealed something profound. Humanity was no longer content to dream in stories alone. Engineers, not just authors, were beginning to sketch starships on blueprints, and yet, behind every proposal lurked the shadow of paradox. If faster-than-light travel were possible, even in principle, then causality itself could fracture signals, could outrun time, arriving before they were sent. A traveler could return before departing, unraveling the chain of cause and effect upon which reality depends. Physicists debated, would nature permit such violations, or would some deeper principle still, unseen, intervene to prevent them? Stephen Hawking called it the chronology protection conjecture, a cosmic safeguard against paradox, ensuring that time's arrow could never be bent too far. It is here that science begins to touch philosophy, for the laws of physics do not only describe motion and matter, they define what it means for events to happen, for the universe to have order. To tamper with the speed of light is not simply to chase a dream of travel. It is to meddle with causality itself. It is to step into the machinery of existence, where one wrong adjustment could unweave the fabric of the cosmos. The discovery phase, then, is not merely about breakthroughs. It is about realizing the depth of the wall humanity faces. Each experiment confirmed the limit, each theory hinted at ways around it, and each attempt revealed new dangers hidden in the equations. Still, the yearning grows. In the silence between stars, in the long echo of radio signals sent toward the void, there is a pull that no obstacle can silence. Humanity is a species that has always reached, whether across rivers, oceans, skies, or planets. It has always believed that distance was not destiny, but invitation. The cosmos stretches out, a cathedral of light, unreachable, and yet the instinct remains. One day, the stars must be touched. The paradox deepens. Every scientific step forward illuminates two truths at once. The dream may be possible, and the dream may be dangerous beyond measure. For now, humanity hovers in this tension. Accelerators push particles to the brink of light. Theoretical physics scribbles warp bubbles onto chalkboards. Telescopes peer at black holes, wondering if their fury hides shortcuts through spacetime. And behind it all, one haunting thought remains. What if the act of trying, just trying, were enough to break something fundamental? The discovery phase is not only about progress, it is about the slow realization that perhaps the universe itself has set a boundary for reasons beyond human comprehension, not to imprison, but to preserve, not to deny the stars, but to protect the fabric that holds them together. And yet, the dream does not die. For as long as the stars burn, humanity will look to them and wonder. This is discovery's gift, and its curse, to reveal both possibility and peril, to promise both wonder and warning. The journey has only begun, but the risks are already visible. The horizon is brighter, but also darker. The dream of light speed has entered the realm of science, and with it, the stakes have risen higher than ever before. The cosmos is not a lawless expanse. Beneath the majesty of stars and galaxies, an invisible structure governs all motion, all energy, all destiny. It is here, in the bedrock of physics, that the dream of light speed collides with reality. At first glance, light seems ordinary. It is the glow of a candle, the shimmer of a sunrise, the spark of a lightning strike. Yet light is unlike anything else in the universe. It is not just illumination. It is the fastest signal that can ever be sent, the ultimate courier of information, the cosmic speed limit written into the fabric of existence. When Albert Einstein unveiled special relativity in 1905, he transformed this flicker into law. No matter how one moves, whether standing still, racing in a rocket, or spinning upon a planet, always the same, immutable, unyielding. This constancy comes at a price. As an object with mass approaches the speed of light, its energy requirement grows without bound. Asterisk, asterisk, this is the double-edged gift of relativity, time travel forward, achieved not through magic, but through motion. Yet it comes chained to impossibility. To reach the speed of light is to demand infinite energy, a resource the universe cannot provide. Particle accelerators confirm this with every collision. Protons, spun to nearly the speed of light, acquire mass thousands of times their rest weight. Their lifetimes elongate, their decay slowed by time dilation. The barrier holds, unbroken, indifferent to ambition. But why? Why does nature defend this boundary with such ferocity? The answer lies in causality. The speed of light is not arbitrary, it is the maximum rate at which information can propagate. If one particle could exceed it, signals could leap backward. In time, cause could follow effect. Paradoxes could unfold where an action undoes itself before it occurs. The sequence of reality, the logic of before and after, would collapse. Imagine a world where an astronaut sends a message home before leaving, where destruction precedes creation, where the arrow of time becomes a closed loop, endlessly devouring itself. Such scenarios are not merely absurd, they are violations of the very mathematics that allow the universe to be coherent. This is why the barrier exists. It is not just physical, it is metaphysical, a safeguard, a firewall of causality. Yet within this limit, the universe bends in astonishing ways. As an object accelerates, distances along its motion contract. A starship approaching light speed would see the galaxies ahead squeezed together, the cosmos compressed into a tunnel of light. What seems unreachable across eons might shrink into a journey of decades, even years. The price is time itself. The travelers may reach Andromeda, but when they return, millions of years may have passed upon Earth. Thus, the barrier is not only a wall, it is a mirror. It shows humanity that reaching the stars may be possible, but never without cost. Physicists have explored the fringes of this boundary with thought experiments. Tachyons, hypothetical particles that always move faster than light, were once proposed. But their existence collapses into paradox, their equations unstable, their implications chaotic. No experiment has ever glimpsed them. The universe seems to conspire to erase them from possibility. Black holes, to reveal the rigidity of the limit. At the edge of a black hole lies the event horizon, the point where even light cannot escape. Nothing can exceed light speed, so nothing can outrun the inward pull beyond this line. Here, relativity does not merely set a limit, it sculpts the most extreme structures in existence. And still, nature tempts. Quantum physics suggests loopholes that seem to whisper of escape. Entanglement allows particles to share states instantaneously, as if distance were irrelevant. Virtual particles flicker into existence from nothing, defying classical expectation. In these shadows, some glimpse the faint outline of faster-than-light phenomena, but entanglement does not transmit usable information. Virtual particles vanish before they can be grasped. The loopholes close as quickly as they open. The physics of the limit, then, is more than mathematics. It is a narrative written into the bones of reality. Speed is not merely motion, it is a measure of how deeply one can cut through space-time without unraveling it. The light barrier is not an arbitrary hurdle. It is the condition that makes cause, effect, and order possible. For humanity, this truth is both devastating and profound. The stars may remain beyond reach, not because of weakness or lack of ingenuity, but because the universe itself requires consistency. The very fact that events can unfold, that memories can be recorded, that existence can be coherental, of it relies upon this inviolate boundary. And yet, the dream endures. The wall is solid, but walls invite challenge. Even when physics declares impossible, imagination continues to search for cracks. Alcubierre, warp bubble, traversable wormhole, exotic matter, and negative energy. Each one dances at the edge of relativity, exploiting the geometry of space-time itself to slip past the limit. But each too carries warnings. They demand substances unknown, energies inconceivable, and risks immeasurable. They suggest not only the possibility of travel, but of collapse, of tearing at the fabric that holds galaxies in place. Thus, the physics of the limit is not the end of the story. It is the dramatic center, the point where humanity realizes that its greatest dream may require defying the very structure that gives reality meaning. The cosmos does not forbid lightly. If the speed of light is a law, then it is one written in fire across the stars, enforced by paradox, defended by infinity. To reach beyond it may be to enter a realm where reason falters, where time unravels, where even the definition of existence grows uncertain. And yet, history shows a pattern. Every boundary once deemed absolute sound, flight, orbit, has eventually been crossed. The speed of light may prove different, or perhaps it too is only a frontier, awaiting a deeper understanding. For now, humanity stands at the edge of knowledge. The equations are clear. The experiments are decisive. The barrier is real, but the stars still burn in silence, as if daring their watchers to try. The physics of the limit reveals not only what cannot be done, but why the dream matters. To confront this wall is to confront the essence of existence. To test its strength is to ask the most dangerous question of all. What happens if the universe's most sacred law is broken? For as long as humanity has stared upward, the stars have been more than distant lights. They have been destinations. Ancient sailors used them to cross oceans. Poets used them to measure longing, and scientists dreamed of touching them. But the deeper we understood the universe, the more impossible the dream appeared. The wall of light stood immovable, and yet history shows us this. When faced with the impossible, humans rarely turn away. We press forward. searching for cracks in the stone. The first cracks appeared not in science fiction, but in mathematics. In 1994, Miguel Alcubierre, a young physicist in Mexico, wrote an equation that seemed to change everything. He asked a question, both daring and precise. What if we could move not by accelerating through space, but by bending space itself? The idea was simple to state, almost impossible to believe. Relativity had already revealed that space-time is flexible, that stars bend light, that massive bodies warp geometry. Alcubierre imagined a spacecraft that would remain motionless within a bubble of space, while the bubble itself surged forward. Space behind the bubble would expand. Space in front would contract, carrying the craft like a surfer on a cosmic wave. Inside the bubble, no laws would be broken. The ship would move slower than light relative to its bubble. But the bubble itself, as a patch of space-time, could travel faster than light without violating relativity's equations. It was called the warp drive for the first time. The impossible seemed to have a formula. Science fiction had sketched it for decades. Now physics had written it into the language of Einstein's own theory. But beauty carried a curse. Alcubierre's equations required something the universe had never been known to provide: negative energy, not just a little, an amount equal to the mass of an entire star. Exotic matter, with properties that repelled rather than attracted, was the only fuel capable of powering the warp bubble. Without it, the drive was fantasy. With it, the risks were staggering. Negative energy, if it could exist in usable form, might unravel space-time itself. The very fuel for the dream might also be the spark for collapse. Yet the idea did not die. NASA physicist Harold Sonny White revisited Alcubierre's work in the early 2000s, suggesting tweaks that could reduce the energy requirement from stellar to planetary scales. Still beyond reach, but not infinite. A reminder that impossibility sometimes shrinks under imagination. Warp drive was not the only attempt. Wormholes' cosmic shortcuts through space-time offered another. The mathematics of general relativity allowed for tunnels linking distant regions of the universe. Like bridges across impossible gulfs, the concept was intoxicating. A spacecraft entering one mouth could emerge instantly at the other, crossing galaxies in the blink of an eye. For decades, wormholes remained the most elegant dream of faster-than-light travel. But here, too, physics was ruthless. Wormholes, if they existed, would collapse faster than light itself could traverse them. To remain open, they too required negative energy. Exotic matter was no longer just an idea. Were tachyons, those phantom particles theorists once imagined, always traveled faster than light. They were mathematical curiosities, emerging from equations like shadows cast by a flame. But every attempt to detect them ended in silence. They seemed less like inhabitants of reality and more like warnings from mathematics itself. This way lies paradox, and still the efforts continue. Physicists studied quantum entanglement, where particles share a connection so deep that their states appear linked instantaneously, no matter the distance. Einstein himself called it spooky action at a distance. Could this be the loophole, a way to transmit information faster than light? The answer was no. Entanglement could share correlations, but not messages. The universe again slammed the door. Information, the one thing that defines cause and effect, could not outrun light. But these failures were not wasted. Each attempt deepened humanity's understanding of the wall itself. It showed that faster-than-light travel was not simply forbidden out of cruelty, but because it sits at the heart of reality's logic. Every time a loophole appeared, paradox rushed in like a storm, threatening to rip the sequence of cause and effect to pieces. The pursuit itself became almost mythic. Scientists knew the odds were slim, but still they searched, not because they believed the wall would fall easily, but because the act of pushing against it revealed truths even more profound. Warp drives taught us about space-time's flexibility. Wormholes revealed the cosmic architecture that might connect distant galaxies. Tachyons illuminated the fragility of causality. Entanglement forced us to rethink the very meaning of information, the dream of breaking the light barrier. Even in failure enriched science. It gave us more than formulas. It gave us visions. Yet, for the public, the story was different. Movies, television, novels, they carried warp drives and wormholes into culture as if they were inevitabilities, not impossibilities. Starships leapt from star to star. Heroes bent the laws of nature with the flick of a switch. Fiction blurred into aspiration. And here lies the strange paradox of humanity's first attempts. Scientifically, every path demanded the impossible. But culturally, these very impossibilities fueled imagination like nothing else. The harder the wall pushed back, the brighter the dream burned. For when humans face limits, we do not only measure equations, we tell stories. And stories have a power equations do not. They prepare the mind for futures that seem absurd today, but inevitable tomorrow. Consider flight. For centuries, heavier-than-air machines were called impossible. The mathematics of the 19th century declared them absurd. And yet, within a few generations, the sky was filled with wings of steel. Might the speed of light to one day fall? Or is this barrier of a different kind, one not of technology, but of ontology, woven into reality itself? The first attempts could not answer. They offered only possibilities, shimmering just beyond reach, and the haunting sense that perhaps the dream of the stars was less about breaking the wall and more about learning what it meant to live with it. And so humanity stood at a threshold. The stars glittered as they always had. The wall remained unbroken. The equations demanded obedience. But imagination refused. The first attempts were not failures. They were opening notes. The sound of humanity pressing its ear against the wall of light and whispering, "There must be a way." Silence folds across the cosmos like a curtain drawn between realities. In this silence, space is not empty, and time is not steady. They are threads of one vast fabric, stitched together in Einstein's vision of relativity, a tapestry where motion bends geometry and energy twists the very shape of existence. To travel at the speed of light is not merely to move quickly, it is to press against the loom of reality itself. And when matter strains against this limit, space-time begins to warp. Imagine the universe as a still pond. A single pebble dropped into its surface creates ripples, delicate arcs spreading outward. But a ship, accelerated toward light speed, is not a pebble, it is a hammer striking the pond with impossible force. Waves become whirlpools, distortions churn into turbulence. The once stable surface twists into something unrecognizable. In Einstein's equations, this turbulence emerges as time dilation and length contraction. A clock racing close to light ticks slower than one at rest. Distances shrink, compressing in the direction of motion. For the traveler, seconds stretch into hours, and miles collapse into inches. The ordinary scaffolding of reality, time, space, causality, fractures under the strain. To outside observers, the traveler's world becomes alien. A body near light speed appears frozen, stretched into the abyss, half vanished into the horizon of possibility. To the traveler, the rest of the universe accelerates away, rushing toward its own future. Space-time itself becomes asymmetric, distorted, not in metaphor, but in measurable fact. The distortions are not gentle. They carry paradoxes, sharp as broken glass. If one could ever reach the light barrier, relativity insists that mass would grow without bound. A gram of matter would weigh more than stars. The energy required would swell toward infinity, threatening to collapse into singularity. The engine striving for light speed would become a black hole in its own right, devouring itself, devouring space, devouring time. Physicists describe this not with fear, but with equations. The Lorentz factor, gamma, grows larger as velocity approaches light. At everyday speeds, gamma is close to 1. At 90% the speed of light, it doubles. At 99.999%, it grows thousands of times larger. Each digit added to the velocity becomes a dagger, aimed at reality's fabric. But mathematics is not enough to capture the strangeness. Consider the traveler's perception. The stars ahead blur into a single beam, compressed by relativistic aberration. Cosmic rays, harmless at low speeds, now strike like torrents of radiation. Deadly bullets, released by distorted space-time itself. Ahead, a glowing wall of light forms photons, unable to outrun the traveler, pile up into a searing barrier. Behind, the universe darkens, stretched into silence. The distortions cut deeper than physics. They gnaw at causality itself. If time slows for the traveler, if distances collapse, then what of cause and effect? Can an action still precede its consequence when the order of events shifts with velocity? If space-time is twisted enough, the arrow of time could loop back upon itself. A ship meant to be a vessel becomes a paradox engine, unraveling the sequence of history. Speculative physics takes this further. In some interpretations, exceeding light speed could fracture space-time into tachyonic domains, regions where particles move backward through time. What begins as exploration becomes contamination, the traveler leaking paradoxes into the continuum. One experiment, one journey, could seed an instability that spreads outward, shredding causality across the cosmos. Einstein himself warned that the speed of light was not simply a technological barrier, it was a law of reality to disobey. It would not mean breaking a rule. It would mean destroying the playing field on which rules exist. This is why physicists speak of space-time distortions with awe and unease. A rocket is not merely an object in motion. It is an anchor pulling on the geometry of the universe. Push too hard, too far, and geometry itself tears. The question is no longer whether humanity could build such a machine, but whether the universe could survive its passage. And yet, hidden in this darkness is wonder. To stand near the edge of light speed is to glimpse what Einstein glimpsed. The revelation that reality is flexible, not fixed, that time itself can bend, that space can fold, that existence is not absolute but relational. This dream lures physicists and dreamers alike, even when its cost may be infinite. The fabric of space-time is both cradle and cage. It allows galaxies to dance, stars to burn, and life to emerge. But it also imposes its merciless speed limit. To strain against it is to gamble with the very texture of being. For perhaps, just perhaps, one experiment to reach the speed of light would not end with a journey, but with a collapse, a ripple spreading outward until the entire tapestry comes undone. And in that silence after, when the last distortion fades, the universe itself may vanish like a reflection shattered on the pond. In the silence of the cosmos, energy is the only true currency. Stars spend it in torrents of light and heat. Galaxies hoard it in their cores, and black holes swallow it in an endless hunger. Every motion, every transformation, every flicker of life is a transaction written in the language of energy. Humanity's dream of breaking the light barrier is not exempt. To push even a fraction closer to the speed of light climbs beyond measure. It begins with Einstein's simple but unyielding revelation. As an object moves faster, its mass is no longer fixed. It swells invisibly, as if the very fabric of reality resists its motion. The closer it comes to light speed, the heavier it grows, until a single gram of matter carries the inertia of worlds. To accelerate that growing weight requires ever greater force and thus ever more energy. At 99% of light speed, the demands are titanic. At 99.9%, they are astronomical. And at the edge itself, the numbers diverge into infinity. Consider a thought experiment. Take a spacecraft no larger than a car and try to drive it toward light speed. To push it to 99% would demand more energy than the entire world consumes in a year. Push it further, 99.999, and the required fuel surpasses the output of every power plant humanity has ever built, combined across all of history. In that cold arithmetic, physics speaks clearly. The barrier of light is not a wall to be shattered, but an abyss that grows deeper with every step closer. The comparisons grow more unsettling the larger the vessel. A shuttle-sized spacecraft, accelerated to relativistic speeds, would demand fuel reserves that exceed the lifetime energy of the sun. To carry such fuel would require another sun, and another to carry that one in a chain of impossibility. Even the greatest civilizations imagined in science fiction, harnessing the power of galaxies, would find themselves pressed against this unbending rule. But the cost is not only in propulsion. At near light speeds, the universe itself becomes hostile. Empty space is not empty at all, but filled with a thin mist of atoms and dust, relics of stars long gone, hydrogen scattered across the void. To a ship drifting slowly, they are harmless. But to a vessel moving at relativistic speeds, each stray particle becomes a bullet, each atom a bomb. A single collision with a lone hydrogen atom at those speeds would release the energy of a nuclear explosion. Space, once serene, transforms into a minefield of invisible detonations. Shielding against such fury demands still more energy. To survive at the edge of light is to fight not only inertia, but the universe itself. Radiation flares, particle impacts, magnetic storms, each one multiplied by motion until even the emptiness becomes deadly. A starship attempting such a voyage would not merely need power to accelerate. It would need power to protect itself from the very medium it moved through. The faster it fled, the fiercer the universe's resistance would grow. This relentless escalation leads to a darker reflection. Energy, after all, is what binds existence. Stars shine until their fuel runs dry. Life thrives only while food and sunlight sustain it. Even the growth of galaxies depends on the steady exchange of energy between stars, gas, and gravity. In every case, the end comes when the cost can no longer be paid. To chase the speed of light is to ask for a resource the universe may never provide, to demand more energy than the cosmos has allotted to any single act. Philosophers of physics sometimes wonder, is this nature's safeguard? A barrier not just of mechanics, but of meaning. The infinite energy required to reach light speed may not be an accident of mathematics, but a deliberate boundary woven into the fabric of reality. It is as if the universe has whispered, "Here and no further." To cross this line would not be merely to travel faster. It would be to rupture the very accounting that keeps existence in balance. And yet, speculation lingers. What if there were a way to cheat? Could exotic matter, negative energy, or warped spacetime itself allow a vessel to bypass the impossible cost? Theories abound, but all share the same unease. To pay the price by any means is to tamper with forces that do not forgive mistakes. The dream of faster-than-light travel may not be barred because it is difficult, but because it is dangerous. For energy is not only power, it is order, it is stability. It is the scaffold upon which time, space, and matter rest. To demand an infinite amount, to drain more than the cosmos can yield, may not simply be impractical. It may unravel the laws that bind the universe together. The vision of humanity streaking across the stars is one of wonder and hope. But hidden beneath it lies this stark arithmetic. To light the engines of a starship, to push even 1% closer to light, is to wager everything against the universe's unyielding ledger. And so the question lingers, haunting and unresolved. If infinite energy is the price of breaking the light barrier, is it truly a frontier waiting to be crossed? Or is it the universe's quiet warning that to pursue this dream is to court a cost that no civilization should ever be willing to pay? Time is the silent river upon which all events drift. Cause leads to effect. The seed becomes the tree. The spark becomes the flame. History unfolds in a single, unbroken direction, or so it seems. At ordinary speeds, the current is gentle, predictable, unyielding. But when motion pushes close to the speed of light, the river begins to twist. Its flow bends, its order wavers, and with it, the very idea of cause and effect trembles. Einstein's special relativity revealed that time is not absolute. It is pliant, shaped by velocity and gravity. To observers moving at different speeds will not agree on the same tick of the clock. A second to one may stretch into minutes for another. For those who remain at rest, time marches on. For those who ride the brink of light, it slows, softens, dilates into near stasis. The implications are astonishing. A traveler launched toward the stars at near light speed might return to Earth after what feels like only a few years, only to find centuries have passed at home. This is not fantasy, it is physics, confirmed in particle accelerators, where unstable atoms, racing at relativistic speeds, live longer than they should. Time itself bends for them, preserving their existence against decay. Yet this gift carries unease. If time can stretch, can it also break? Could an object moving faster than light not only traverse space more quickly, but slip backward into history? According to the mathematics, the answer is unsettling. Yes, messages could arrive before they were sent. Effects could appear before their causes. The universe's most sacred order, that the past is fixed, the present unfolding, and the future unwritten, would dissolve. This paradox takes form in thought experiments. Imagine a signal transmitted faster than light, sent across space to a waiting receiver. In one observer's frame, the message travels forward in time, arriving after it was dispatched. But in another's, moving at a different speed, the order reverses. The message arrives before it was sent. Now the receiver could reply before the first transmission occurred, creating an infinite loop where communication writes itself. Information exists without origin, a whisper from nowhere. Extend this further, and the contradictions grow darker. If a spacecraft could surpass light speed, it might arrive at its destination before it departed. The traveler could watch their own ship leave an echo folded into reality. In theory, one could even intervene in the chain of events that led to the voyage, undoing their own journey before it began. The so-called grandfather paradox emerges here, the nightmare of altering a past that should be immutable. Such scenarios are more than curiosities. They threaten the logical skeleton of reality itself. If causality can fracture, the universe loses coherence. Laws dissolve into paradox, history into contradiction. Physicists call this the causality problem, the simple truth that faster than light motion, while mathematically intriguing, unleashes consequences that reality itself cannot seem to tolerate. And yet, the idea persists. Some propose that the cosmos possesses built-in defenses. Perhaps the laws of quantum mechanics weave a safety net, forbidding paradoxes before they occur. This is the essence of the chronology protection conjecture, suggested by Stephen Hawking, that the universe, by its very nature, prevents the formation of time loops. Whenever conditions arise that might permit causality violations, some deeper mechanism intervenes, sealing the breach. Exotic matter collapses, wormholes destabilize, energy demands explode to infinity. In every case, the universe finds a way to preserve order. Still, questions linger at the edges of theory. Quantum entanglement, for instance, allows particles separated by vast distances to act in perfect synchrony. Some interpret this as a kind of superluminal influence, a whisper that transcends space and time. Yet no usable information ever travels faster than light. The paradox remains contained. It is as though the universe permits hints of timeless connection, but never enough to unravel causality. In the speculative reaches of physics, researchers toy with models of tachyons, hypothetical particles that always move faster than light. If they exist, their very nature would be paradoxical. they would move backward through time as effortlessly as forward. But every attempt to incorporate tachyons into consistent theories collapses under contradictions. The mathematics rebels, the physics breaks. It is as though reality itself refuses their existence. The paradox of causality does more than warn against faster-than-light travel. It raises a deeper, more haunting question. Is time itself an illusion, a construct of perspective rather than a fundamental truth? If motion and speed can bend the flow of moments, if faster-than-light motion could unravel it entirely, then perhaps time is not the river we imagined, but only the shadow of something deeper, a geometry of space-time in which cause and effect are emergent, fragile, provisional. For humanity, the dream of outrunning light was always about freedom, freedom from distance, from isolation, from mortality itself. But in the realm of causality, the dream curdles. To break the light barrier may not only free us from the chains of space, it may unbind us from the order of time. And in that unbinding, meaning itself may vanish. If effects can precede causes, if history can rewrite itself, then existence becomes a hall of mirrors, endlessly reflecting, without origin or end. It is here that the dream of light speed begins to feel less like aspiration and more like warning. The cosmos may allow us to stretch time, to delay decay, to drift centuries into the future with only years upon our own clocks. But it seems to draw the line at reversal. The arrow of time, once broken, unravels everything. And so, just as infinite energy guards the speed of light, infinite contradiction guards the sanctity of causality. The paradox whispers its quiet truth. Faster-than-light motion is not merely expensive, not merely perilous. It is forbidden, not by decree, but by the very logic that sustains reality. And if the cosmos is a story written in stars, bound in galaxies, told in the breath of time, then causality is its grammar. Break it, and the story ceases to make sense. Every horizon promises discovery. From the sailors who first pushed past the edge of known seas, to astronomers who peered beyond the faint stars of antiquity, the act of crossing boundaries has always defined humanity. But the universe holds a horizon far stranger than any ocean, one not of geography but of physics, a boundary etched into the very fabric of spacetime. A place where laws bend, where knowledge falters, where even light itself is denied passage. This is the event horizon, the ultimate frontier, born from the collapse of massive stars. Black holes are regions of spacetime so steeply curved that no escape is possible. Their surfaces are not surfaces at all, but thresholds. Cross the horizon, and every path, every possibility, every future leads inward. To an outside observer, a traveler approaching this edge appears too slow, frozen against the darkness, their final moments stretched into eternity. But for the traveler, nothing unusual occurs as they pass the boundary. The fall continues, inexorable, silent, into the abyss. That the event horizon is the most absolute barrier known to science. No signal can cross outward. No information can be retrieved. To look at a black hole is to stare at a one-way gate, a horizon into which the universe itself vanishes. And yet, paradoxically, it is here, at the threshold of the unknown, that some of the deepest questions of physics are written. The puzzle begins with information. Quantum mechanics teaches that the universe is built upon conservation, that the state of every particle, every interaction, is never truly erased. But black holes seem to mock this principle. When matter falls past the horizon, its identity vanishes. The atoms, the structures, the very details of what it once was are erased from the visible universe. According to classical relativity, they are gone forever. Their only legacy, the silent increase of the black hole's mass. But if this is true, then information is destroyed. And if information can be destroyed, the foundations of physics collapse. Predictability itself disappears. The universe ceases to be a lawful system and instead becomes a chaos where the future cannot be deduced from the past. This crisis, known as the black hole information paradox, has haunted physicists for decades. It pits two of the most successful theories ever devised, general relativity and quantum mechanics, against one another in a conflict neither can win. Relativity declares the horizon absolute. Quantum theory insists that information cannot vanish. Both are correct within their realms. Together, they erupt into contradiction. The paradox deepened in 1974, when Stephen Hawking made a startling discovery: black holes are not entirely black. Through subtle quantum effects at the event horizon, they emit faint radiation, a thermal glow, now known as Hawking radiation. Over vast timescales, this radiation drains the black hole of mass until it evaporates completely. If Hawking was right, the ultimate fate of a black hole is to vanish, leaving behind only the ghostly afterglow of its radiation. But in that final fading, what becomes of the information swallowed inside? If it does not escape, it is erased forever, in direct defiance of quantum law. If it does escape, then somehow the event horizon must not be as absolute as relativity demands. The horizon, it seems, conceals not only matter but truth. To resolve this mystery, physicists have proposed daring possibilities. Some suggest that information is smeared upon the horizon itself, encoded in subtle patterns of quantum entanglement, the so-called holographic principle. In this vision, the three-dimensional universe we know may itself be a kind of projection, its information written upon a distant cosmic horizon. Others argue that wormholes, quantum tunnels linking black holes across spacetime, may carry information away in secret. Still others claim that Hawking radiation itself may whisper the missing details, too faint for us to detect, but preserving the law in ways we cannot yet measure. And yet, none of these ideas is proven. The paradox remains open, unresolved, like a riddle left by the universe itself. Event horizons also mark the limits of observation on a grander scale. The expansion of the universe creates a cosmic horizon, a boundary beyond which light from distant galaxies will never reach us. With every passing moment, space itself stretches, carrying distant worlds farther away. Beyond a certain point, their light is receding faster than it can arrive. They slip over the edge of visibility, erased, not by gravity, but by the relentless growth of spectrometry. It's here too lies a horizon of the unknown. Are there galaxies, civilizations, perhaps even entire cosmic structures forever beyond our sight? Their existence is undeniable. Their presence is eternal. But for us, they might as well not exist. The horizon defines the edge of our universe, not because reality ends there, but because knowledge does. The resonance between these horizons is profound. One carved by gravity, the other by expansion. Both represent boundaries where the human quest to know is silenced. They are reminders that reality has limits, that there are places the mind may imagine but never reach, and yet, paradoxically, it is precisely at these limits that our imagination flourishes. Horizons haunt philosophy as much as physics. To cross them is to dream of breaking the absolute. To accept them is to live with mystery. Black holes, event horizons, cosmic boundaries. These are not merely scientific constructs. They are symbols of the human condition, of a species forever caught between curiosity and limitation. Every horizon forces a question: what lies beyond? For the sailors of Earth, the unknown meant new continents, new worlds. For physicists, horizons mean something deeper. They mark the boundary between knowledge and ignorance, between order and chaos, between science and speculation. To stare at a horizon is to confront the edge of understanding itself. Perhaps, in some distant future, we will learn to read the whispers of Hawking radiation, to decode the holographic script of the horizon, to glimpse across the cosmic divide. Or perhaps horizons are eternal, barriers that no intelligence, however advanced, can transcend. For now, they remain silent, their edges sharp against the infinite. And in that silence lies both awe and humility. Horizons remind us that the universe is not ours to command, but ours to witness. Not a book to be finished, but a mystery that deepens with every page. The horizon is where knowledge ends and wonder begins. There are places in the cosmos that feel less like destinations and more like warnings, places where the mathematics of nature builds walls so high that even imagination strains to climb them. They do not simply resist entry, they forbid it. These are the forbidden frontiers, thresholds that beckon with mystery yet declare, with silent gravity, do not cross. For most of history, humanity's boundaries were geographic. Oceans, mountains, deserts, each one a line that seemed impassable until curiosity demanded it be breached. And time and again, the barrier fell. New lands opened. New maps were drawn. The frontier was always an invitation. But in physics, there exist barriers that are not invitations at all. They are ultimatums. The speed of light, the singularity within a black hole, the cosmic horizon where space-time itself retreats. These are thresholds not carved in sand, but in the bedrock of reality. To approach them is to discover not a passage, but a wall. Among these, few inspire more awe or dread than the singularity. At the heart of every black hole, general relativity predicts a place where density becomes infinite, where the fabric of space-time collapses to a point of no size and infinite weight. Here, every known law fails. Equations lose meaning. Concepts like space and time themselves unravel. The singularity is the forbidden heart of gravity, a place where science can no longer speak, no human eye will ever see it, no probe can survive the journey. The singularity is the ultimate do not enter sign, hidden behind the veil of the event horizon. Its very existence may be less a feature of nature than a signal that our theories, magnificent as they are, remain incomplete, that beyond this threshold lies not only the unknown, but perhaps the unknowable. And yet the forbidden frontier is not only about singularities, It is etched into the cosmic speed limit itself. The speed of light, minus 299,792 kilometers per second, is not merely fast, it is final. As objects accelerate, their mass increases, their energy requirements explode toward infinity. To reach light speed would demand infinite energy. To exceed it would shatter causality, allowing effects to precede causes, breaking the chain of time itself. In this sense, light speed is not a challenge, but a boundary, a barrier woven into the very logic of the universe. To cross it would not simply be difficult, it would be nonsensical. The frontier here is not material, but logical, forbidding not by force, but by contradiction. To imagine a reality where the barrier is broken is to imagine a reality where time unravels, where paradox devours cause and effect. Even the cosmos itself presents a forbidden edge. As the universe expands, distant galaxies recede faster and faster. Beyond the cosmic horizon, light emitted today will never reach us. No future telescope, no technology, no intelligence can see past that line. Beyond it, the universe continues. Vast, perhaps infinite, but for us, it is a forbidden realm. Not because it is dangerous, but because it is forever sealed. We know it exists, we know it is real, but it is unreachable, untouchable. A reality that might as well belong to another universe. The forbidden frontier is not simply physics, it is philosophy. It forces a reflection on the limits of knowledge itself. Are these barriers absolute, or are they invitations in disguise, challenges meant to be overcome, like the seas and mountains of Earth's past? Some physicists dream of wormholes, threading space-time, shortcuts that bypass the speed of light. Theoretical constructs like the Alcubierre drive propose bending space itself, compressing the front and stretching the back so a ship could move without moving, carried forward like a surfer on a wave of space-time. Others imagine that singularities might be gateways, not ends, but passages, connecting to other regions of the universe, or even to entirely new universes beyond. But these ideas, however elegant, remain speculative. They are sketches on the blackboard, fragile against the weight of reality. To create a wormhole stable enough for passage might demand exotic matter with negative energy density, a substance no experiment has yet revealed. To warp space-time in a drive might require more energy than exists in the visible universe. And so, the forbidden frontier remains unbroken. There is a haunting beauty in this permanence. For the first time, perhaps, humanity faces barriers not meant to be crossed. Frontiers that do not yield to willpower, to courage, or even to genius. Horizons that say not yet, but never. And yet, in a paradox worthy of the cosmos itself, it is these very prohibitions that drive the greatest creativity. Confronted with impossibility, physicists are forced to rethink reality itself, to imagine new frameworks, new mathematics, new visions of space and time. String theory, loop quantum gravity, holographic universes, all arise from the attempt to understand what lies beyond the forbidden line. The frontier, even if sealed, becomes a source of progress, forcing science to evolve. Perhaps this is the secret role of the forbidden frontier, not to invite crossing, but to provoke wonder, not to yield new maps, but to reveal the limits of the old. It is a mirror held up to human ambition, reminding us that knowledge has boundaries, and that beyond those boundaries lies mystery itself. There is, after all, a kind of humility written into the universe. For every triumph of science, every law discovered, every horizon expanded, there are still regions where the cosmos whispers, "Not here." Places where curiosity must stop at the threshold, peering into the dark, knowing that some truths may forever lie outside the reach of reason. The forbidden frontier is not a failure. It is a message that the universe is not ours to conquer, but ours to witness. That mystery is not an obstacle to knowledge, but its most essential companion. Without the forbidden, there would be no wonder. Without boundaries, there would be no questions. And so humanity stands, as it has always stood, at the edge of a horizon, staring across an ocean it cannot sail, into a darkness it cannot pierce, toward a silence it cannot break. The frontier looms vast and silent, its message clear as starlight. There are places you cannot go, not because you are unworthy, not because you are unready, but because the laws of reality have spoken. The forbidden frontier is where the cosmos itself says, "Here you must stop." And in that stopping, in that silence, in that awe, the human story continues.